Hi everyone. In this part of the lecture, we are going to consider three different second order systems in more details into account and see how we can indeed have an estimate of some basic step response, let's say, parameters such as rise time, settling time, and so on and so forth. We first start by the overdamped systems. In the case of overdamped systems, we know that the poles that we have for the system are located at minus zeta omega and plus minus omega n times square root of zeta squared minus 1, and both of them are real and negative, and this happens for zeta bigger than 1. So something like this as an example. Yeah, we have one pole here and the other pole over here. We have the overdamped case. Then we can define the time constants t1 and t2 in the form of ti equal to minus 1 over pi, which are associated to the poles, and the transfer function could be rewritten in this form. So g of s will be rewritten in the form of 1 over 1 plus s times t1 times 1 plus s times t2. And therefore c of s will have this form, yeah? 1 of s times g of s, and then we can find the unit step response of the system in the time domain. We will get it written as here. So 1 minus t1 over t1 minus t2 times e2 minus t over t1 plus the third term. Then for the overdamped case, if we assume that t1 is much bigger than t2, so t1 is much bigger than t2 means that t1 minus t2 is much bigger than 0. And then we can kind of rewrite what we have over here. So since t1 minus t2 is quite big, then we can say that t1 over t1 minus t2 could be approximated as 1. Because t2 is much smaller than t1, then the difference that we have here, t1 minus t2, could be approximated as t1, and as a result, t1 over t1 will be equal to 1. On the other hand, the term that we have here, t2 over t1 minus t2, could be approximated by 0, because t1 minus t2 is much bigger than t2, let's say. Okay, so this term will be approximated as 0, and t1 over t1 minus t2 could be approximated as 1. If we do so, the approximate step response that we have will be written in the form of 1 minus e2 minus t over t1. And you know that this is a step response similar to the step response of a first order system, with the time constant equal to t1. And since we know the rise time and settling time expressions for the first order systems, we can use the same expressions in order to find the rise time and settling time of this kind of second order systems. So this is valid for the overdamped systems. So we can approximate an overdamped system with a first order system. How valid our approximation is will depend on the values that we have for t1 and t2. How big is the difference between them? Over here we have two examples. For g1 we have 1 over 1 plus 5s times 1 plus s, and for g2 we have 1 over 1 plus 5s times 1 plus 0.5s. And this example will show us, as the difference between t1 and t2 increases, as t2 becomes smaller and smaller with respect to t1, the approximation will improve. So in the first case, for g1, we have t1 equal to 5, t2 is equal to 1. In the case of g2, we have T1 equal to 5 and T2 is equal to 0.5. So T2 is much smaller than T1 in the second case compared to the first case. However, for both cases, we can approximate the system as 1 over 1 plus 5s, T1 equal to 5. And here you can see how good is our approximation. What we have in the green color is for the first order system. Or the approximate system that we are going to use for the system. And the one in blue is the exact step response of the system. So this is what we have for G1, and here you can see what we have for G2. If you compare them with each other, you can see that the exact value that we have for the G2 is closer to the approximate one than what we have for G1. Because in the case of G2, the difference between T2 and T1 is bigger. So that's what we have for the overdamped case. Then in the case of critically damped systems, we know that happens for zeta equal to 1. There are two poles at the same location at minus omega n. Both of them are real and negative. We can define the time constant as minus 1 over omega n and rewrite the transfer function for the system in the form of 1 over 1 plus s times t squared, which will give us the step response as 1 over s times the denominator, or 1 plus s times t squared. And then we can find out the step response for the system in the form of 1 minus e to the power of minus t over t plus t over capital T times the exponential term. So this is what we get for the critically damped systems when the poles are at the same location. And for this critically damped system, we can find out the rise time, settling time for 2% and 5%, referring to the expressions that we have here. On the other hand, this kind of system, the critically damped system, could be used as an approximate case for the underdamped systems when T1 and T2 are close to each other. So let's say we have a system with two poles which are pretty close to each other. Then we can approximate this system with a system which has two poles right at the same position. We have an example over here to see how good our approximation would be depending on the values that we have for T1 and T2. For G1, we have T1 equal to 0.8, T2 equal to 3.2, and for G2 we have 2.5 and 1.5 as the time constants. So both G1 and G2 are the overdamped systems. And we want to approximate them with a critically damped system. Both of them could be approximated with a critically damped system which has T equal to 2. So for this case we have a single T which is equal to 2. And then over here you can see how good the approximation is. In the first graph here, what we have in blue is the exact response of the system. The exact response of the system for G1, where we have T1 0.8 and T2 3.2. And what we have in green, so this graph here, what we have in green is the approximate response or a critically damped system with T equal to 2. So here we had T1 0.8, T2 3.2, while in the second case for G2 we have T1 equal to 2.5 and T2 is equal to 1.5. You can see the difference over here. So T2 minus T1 is equal to 1.5 minus 2.5, and the absolute value will be equal to 1. While in the second case, T2 minus T1 is equal to 3.2 minus 0.8, and this will give us 2.4. So the difference here is bigger, the difference here is smaller. As the difference between T2 and T1 becomes smaller and smaller, the approximation that we have for the system will improve in it. Yeah? And you can see here that the blue and green one are kind of behaving very similar to each other. While in the case of G1, where T2 minus T1 is equal to 2.5, they are different at the beginning at least. So this is something to keep in mind, as the difference between T2 and T1 becomes smaller and smaller, the approximation improves. So we approximate an overdamped system by a critically damped system, for which we know the relation between the rise time and T and settling time and the time constant. Now we will have a look at the underdamped systems. You know that for the underdamped systems, the location for the poles of the system will be something like this. So they will have complex values. They will have both real and imaginary values. If we consider the step response of the second order system in the general form, we will have these expressions. So C of S will be in the form of A1 over S plus A2 times S plus A3 at the numerator over the denominator, which should be familiar for you. Now, since we want to consider the underdamped systems, we will have the case where zeta is between 0 and 1. Okay, so this is what we have as the assumption. And then C of S could be rewritten in this form, where A1, A2, and A3 are replaced by their actual values. A1 is equal to 1, and A2 is equal to 1, A3 is equal to the term that you can see over here. And then if you take the inverse Laplace transform, we will get C of D written in this form. So 1 minus an exponential term times a cosine term plus a sine term with some coefficient. And then we can rewrite this in a more compact form as C of D equal to 1 minus a term, a coefficient, times an exponential term times a cosine term. You can see that phi is also a term that depends on the value of zeta only, okay, as the phase. Now, having this expression in hand, we can see how the step response of the second order system for the underdamped systems will look like depending on the value of zeta. Here we have several graphs which are drawn depending on the value of zeta. Here zeta is equal to 0.1, then 0.2, 0.4, 0.5, 0.6, 0.8, and so on and so forth. You can see that as zeta becomes smaller and smaller, the amount of the oscillations increases, the amplitude that we have for the oscillation. And as zeta goes towards 1, the step response of the system looks more like the one of the critically damped system. As zeta goes towards 0, the response looks more like the undamped systems, where we have oscillations that never end. So that's how the step response of the second order system In the underdamped case, we look like, and you can see that it all depends on the value of the zeta. And we again assume that zeta is between 0 and 1 in this case. In the next lectures, we will have a look at how the step response parameters of the second order systems will be defined and how they could be calculated. Thank you for watching this video lecture.